And continuing. So symmetry dictated that we'd have another line flipped over this line. And what we would see if we started drawing additional lines here, we would get a picture that would start to look like this. And we could go and do the individual construction of every point on this in order to see that this is what it would indeed look like. But we would be here literally to the end of time if we wanted to do that. So I'm not going to draw it, and we're going to just do this extrapolation. Right, so what is the mathematical shape of these lines? You'd be very tempted maybe to say parabolas. They're not, right? There's a much more complicated mathematical shape. It's actually a family of curves called a dipole, but we're not going to go into that. But this is what the field looks like in a region where there are a positive and a negative source charge between two source charges of equal strength. In a second video that is going to be posted, or I guess a third video now that I've interrupted this first one, I'll show what happens when these two don't have the same magnitude and how the picture gets skewed. It'll be easier to do on that simulation. So let's next go to what does this look like if, once again, we have charge 1 is positive, but charge 2 now is also positive. So in general, our electric field is going to radiate outwards from both these particles. So let's do that work. So let's pick the point equidistant between them. We know that charge 1 would have an electric field that would push a hypothetical positive particle to the right here, but 2 would have, and I'm not going to label these because the colors do it, and it's going to start to get very busy. Charge 2 is to the left, radially outward from this is how it would push that. But if these are equidistant from this point, and, this is positive, excuse me, equidistant from this point, and these two charges have the same strength, that would mean these two vectors cancel out, and the net result there is that there would be no electric field at that point equidistant between them. But what about a point slightly to the left or to the right of this? Well, let's go slightly to the left of this, closer to charge 1. Well, in that case, E1 would be a much longer vector than E2, right? Because once again, this would go radially outwards from that point. Therefore, there would be a net effect towards the right. And just in the same way that we did last time, I'm going to draw a cleaner picture down here below as we figure things out. So positive and positive, right? I think therefore we can extrapolate that the electric field on the line between them would go towards that point. Okay, let's find the point. And I'm just going to put an open circle there because at that point the electric field is 0. Even though it's supposed to be exactly 1 point, I do want to show a point that is 0. Okay, great. Meaning if I put a little positive charge there, it would go in this direction. In fact, it would accelerate in this direction. It would speed up, get to this point, and actually, kind of a fun thing, what would it do from there? It would speed up, get to this point. That doesn't mean it would stop there, because now it has velocity. It would shoot past that point and then start slowing down and then stop somewhere and then speed up and then that's actually called the electric pendulum. Kind of fun, or my type of fun. All right, let's look at what happens somewhere over here outside. Well, here E1 is strong in that direction. Here E2 also radially outwards at that direction. Okay, so the net field there does just go radially outward. Oh, that's supposed to be in red. Radially outward. I'm doing the thing in the wrong place. Radially outward from here. That drawing should have been up here, folks. I apologize. All right, and then we can just assume on the other side that that's true. So let's look at what happens at a point equidistant, right, but not on that line, above, right, in the same way we did before. So we're going to have E1 going radially outwards. E2 is going to be the same magnitude, but radially outwards from E2. And so remember in the before, when it was positive and negative, the vertical components canceled out. Here, the horizontal components are canceling out, and I get a net electric field that goes directly to the top of the page. So that's going to be true actually everywhere along that line. And then once again by symmetry, boom. So what would happen there if we had a particle there, both would be pushing it equally like this, meaning it would just move away from both of them if it was positive. Okay, cool. So there we go. So let's pick a point that is, kind of see how we have almost like quadrants here. So we'll pick a point in, say, quadrant 1 in order to figure out what's going on there. So I'll pick this point. So if we notice here, E1 is going to be quite small because it's far, but radially outward from that point. E2 is going to be quite large and radially outward, meaning the net effect is going to be something like that, right? And then what happens from there? Well, let's pick another point there. Let's say a point further up. Okay, so if I have a point that's, say, here, once again, I have my E1 is even smaller. E2 is smaller as well now, and goes like this, and so upwards it goes, right? But notice here, this thing has a component that is to the left. This leftwards component is going to be smaller than this leftwards component because now it is closer to this one than it was before. Meaning, as the particle moves upwards and towards the left, the amount that it goes left reduces over time. In fact, what you should have figured out is that that particle, if it started in quadrant 2, would never cross this line because we know when it was placed in this line, it would go straight upwards because of the canceling of those components. So what you end up with is field lines that look like this in this region, right? They almost look like hyperbola, right? Where this line is asymptotic with this. Because remember, the field lines can't cross each other, right? Because that would imply the particle has choice. And so then by parallelism here, we can complete the picture. And then what's happening over here? Well, mostly what's happening over here is there's going to be at some point where you'll have a straight field line and then it actually sort of bends away like this, right? Because it's being repelled by two things at that point, and then parallelism over this way, okay? So that's kind of neat. And once again, in that simulation I'll show you online, we'll look at what happens when these two do not have the same magnitude. So what would this picture look like if I had two negatives rather than positives? Would the structure of the field change? And hopefully what you said is no, the structure would not change. What would change is every arrowhead would flip. So instead, you would actually, negative and negative is what I'm trying to do here. Negative and negative. And so the field here we would still have the blank spot there in the middle, but it would go outward from there. And on the verticals, it would go inward because it would be drawn inward. Here with the two negatives, our pendulum would be along the y-axis. And here we would have those things looking like asymptotic going in. Okay. Okay, and we can complete the picture that way, that way, that way. I'm just literally drawing the same pattern, but with every arrowhead reversed. So that's what happens. Obviously, these pictures get more complicated when I have 3 source charges or 4 source charges or 5 source charges, right? But all it is drawing out each of the individual vectors due to each of the individual points and doing the vector addition problem. We're not going to do this mathematically because these get really complicated when you have lots of source charges, but we're going to look at this sort of qualitatively as we've done. There is one last charge distribution that we're going to look at. We're going to save that for next week. It's actually going to be our most important charge distribution. So not just one positive and one negative, one or two positives or two negatives, but a different structure. And we're going to talk about why it's important. But I'll give you a hint now. If I were to think about the strength of the electric field in this region, we can see it's strong near the charges, and then it gets weaker as you go away as the field lines get further apart, since we said density was proportional to field strength. Where, let me just go back to where in this region would you say the field is the strongest? Well, hopefully what you would say is with the positive and the negative, you would say close to the positive or close to the negative, and then roughly in the region between has a stronger field strength than what's happening outside here. But because of the way these lines sort of bow out, I think what we could easily see is that the electric field is not constant in this region. Similarly, here, the field is clearly not constant in this region. In this place, the field is not constant. What's problematic about the field not being constant in magnitude? Well, if the field is not constant in magnitude, then the forces experienced by charged particles in this region are also not constant. And why is that a problem? Well, that means if the forces are not constant, the accelerations are not constant, and that means that you can't use kinematic equations when you're doing work with this. In fact, it's very hard to do experiments in regions where forces are constantly changing because it adds a variable to your experiment. So what we need to do is construct a region where the electric field and therefore the electric force on an individual charge is going to be a constant so that we can do experiments. And that's what we're going to talk about next week, is looking at that a place where we can get a constant electric field and then look for implications from there.